Alright guys, welcome back. So today's video is obviously going to be quite long since this packet of notes is 17 pages long, can you imagine? And today we're going to be discussing the different types of organic reactions organic compounds can undergo. So compounds of similar structure have similar physical and chemical properties that are typical for their structure. And in this section we're going to be discussing how these chemical properties that are some of these chemical properties. Compounds of the same functional group, or compounds of the same class, will generally undergo the same types of chemical reactions as each other, and knowledge of these reactions will allow you to predict how they will react, predict the reactivity of specific compounds, and you can sort of get organic molecules based on the fact that you know how you can get from that thing. You can base and using your knowledge of how they react, you can go from one compound to another compound. You can form one. You can form a different compound from the starting material, from any given starting material. So, this is sort of an overview of what we'll cover today. There's certainly a lot to cover, but what helps quite a lot is if you categorize these things. And for me, this starts at the highest order of categorization. We can generally classify the reactions that you'll be studying in this course to four main types of reaction: addition, substitution, oxidation, and esterification or condensation, as it's also known. Those are the four broad types of organic reaction that any compound can undergo, and a lot of these arrows here are just specific types of those things. So without that, with that being said, yeah, here we go. So alkanes are fairly unreactive. That's just a given given how strong the C and the CH bonds are, and they don't really react. You can burn them, and that's about it. However, alkanes are a bit more interesting because you see that double bond can serve as the site of chemical reactivity. I apologize if my audio quality is all over the place. This is what you get for $2 microphone at Walmart. But the CC double bond, we can see here that its bond enthalpy is 614 kilojoules per mole. However, we note that the first bond is 346 and the second bond is 268. Notice here how that second bond is actually a little bit weaker than the first bond, and it's actually that second bond which it's that second bond being weaker that allows it to be a site of chemical reactivity, and therefore these alkenes will generally undergo addition reactions, which basically it's more or less what it sounds like. You add things to saturate the double bond, in this case to unsatuate it. Um, so let's look into a few specific examples. So we can have hydrogenation, which is adding hydrogen to a alkene to form an alkane. Um, it's pretty obvious. You're just adding hydrogen here, and you typically need high heat and transition metal catalysts, so nickel in this case, and heat. So this would be adding hydrogen. So you see that double bond here. If you add hydrogen and under a nickel catalyst with some heat, you get C6H12. And similarly here, you can form ethene into ethane. You can also add halogens to an alkene. So halogenation. So reacting with the halogen. And halogens X2 can be added to a double bond as hydrogen can, and here's sort of an example here with the bromine and chlorine. Propene, if you add bromine to it, you can get 1,2-dibromopropane, and then C6H10, if you add chlorine to it, you can get this molecule here. Sort of an interesting, I don't know if I would call it an aside, but you can use this in the lab to determine the degree of saturation of a hydrocarbon that you don't know what's in it. So say you're given a test tube, you know it's some organic compound, but you don't know what it is. You can use the bromine test to determine saturation. So here, if it's fully saturated, nothing will happen, and note here that bromine is actually red. So bromine is red, so with an alkane, it won't react since, there's nowhere nothing to react with. Whereas if it was an alkene, it would undergo addition, and the product is colorless. So in the lab, what you would see is that red color would slowly fade away and it would disappear. And if that is the case, then you had an alkene to start with. Um, but if that was not the case, then you know it was an alkane. Next, we can sort of combine what we just discussed, and we can do hydrohalogenation, which is addition of a hydrogen halide, HX. Um, there is a bit of for standard levels, you'll always be given symmetric alkanes. For the higher levels, you'll actually learn a rule to predict um, what the major product is and the minor product is, because if it's not a symmetrical one, i.e., one carbon chain is longer than the other one, if the double bond splits it such that one chain is longer than the other one, there is actually a rule to determine what forms. But for standard levels, you don't need to worry about that stuff. You'll always be given something that you can properly use. But for the higher levels, we will discuss it in the next video, actually. The next one we can do is the addition of water. And you can, once you, I don't know, you would technically call this you could consider this hydrolysis. But once you add water into it, you can get an alcohol. So you can turn ethene into ethanol by adding water into it. So a hydrogen would go onto one of these carbons here, and the OH group would go onto another carbon, the other one. Sort of to culminate sort of this sort of addition reaction, we could, okay, fine. Let me try and find a way to introduce this. Okay, so we've seen it for one molecule. What if we wanted to sort of repeat this addition process over and over again? And that's where we get the idea of formation of addition polymers. So polymerization is basically the making of a long string, a long ass molecule that is like hundreds of thousands of carbons long. Basically, you take one small repeating unit and you add it to itself a bunch of times to make a really large molecule. And you'll often see this in biology, where if you undergo condensation and polymerization with amino acids, you can form long proteins that can do specific things, like, I don't know, act as skin or whatever. But in the context of chemistry, that's sort of, you form these long string molecules that are really long. And polymers are made from many small molecules called monomers, and polymers can undergo and when you add them up together, you undergo a process called polymerization. Now, in this case, it would be addition polymerization, in which small alkene molecules or small alkene monomers will undergo a chain reaction to link them together. Some examples of polymers that you might have heard of are polyethylene, PVC, and Teflon. Memorize this chart. I hate to say it, but organic has a lot of memorizing, and this is one of those things where you just kind of have to memorize it. However, the process, it's rather intuitive. So it's not intuitive, but it makes sense once you think about it logically. So the first step would be the initiation step, where you create. So one method is to form a polymer is what we call a radical chain reaction. So the idea here is that we have three steps: the initiation step, the propagation step, and the termination step. The initiation step is creating radicals, and the way you would do this in a lab is by, say for example, you would typically take a halogen, in this case it would be chlorine, put it under UV light, and the UV light will have enough energy to break that bond homolytically, and you would get two chlorine radicals. And then you would react these radicals with you would react it with these alkenes, and you would get larger radicals. So here you have this Cl radical attacking this ethene molecule, and you form a large radical. And when you do that again and again, and then this radical will attack another ethene molecule to form an even larger radical, and then the process sort of repeats. It's literally where the term chain reaction comes from, because once one thing reacts, once you have the chain going, it'll bump into each other and creating larger and larger molecules until eventually, since you had two chlorine radicals, you would get, it would react with more and more carbon chains until eventually, both of those super large radicals met up, and they joined together, and they formed a polymer. So that's the termination step I just described. So an option that is two propagating chains. So that is when two propagating chains, so these things here, combine to make a non-radical. So x plus y equals n, and then you would have this repeating unit. If you wanted to, so okay, fine, we know how to go from monomer to polymer, but what if you wanted to know the specific monomer that made up a polymer? So you'll be given a section of polymer and look for the smallest repeating unit. So here it would be CH2CCl2. So here clearly we can see this is the repeating unit, and then you can just draw out a Lewis structure for that repeating unit that makes it work. So, and in this case, that the carbons would have to be double bonded in this case, but that's sort of how you go backwards from going forwards. Combustion, yeah, there's not much to say here. You can undergo either complete combustion or incomplete combustion. Incomplete combustion means that either some carbon just does not oxidize at all, or you get carbon monoxide forming and not carbon dioxide and water. Water, lots of talking. There's really not much to go there, so let's not do that. The next sort of major type of so we've just covered all the different types of addition reactions that you would be seeing in the standard level syllabus. Now let's do the same thing for for all the substitution reactions that you'll see. And the first one that we'll cover here is the photochemical free radical substitution of an alkane. So generally you have R is just rest hydrocarbon chain, and then H plus a halogen, you would get a halogen alkane plus a hydrogen halide. So specifically, you turn that into that, and then sort of, yeah, that's sort of the general overall reaction, and you're expected to know the reaction mechanism for this particular reaction. So we have three steps similar to the polymerization one. So we have initiation, propagation, and termination. So the initiation step is by using shining UV light onto a sample of gaseous chlorine atoms, and then the propagation steps are basically this chlorine here will attack this hydrogen atom here, and it will essentially steal it from this hydrocarbon chain, and you will get HCl. But since you had two radicals, so that you can either have that, you can essentially have one of those chlorine radicals attack the hydrocarbon molecule and steal a hydrogen from it, and then you would end up with getting a methyl radical. Or alternatively, since chlorine is more electronegative, you can do the initiation step with the methane and get a methyl radical, and you can form a hydrogen radical and a chlorine hydrogen radical, and then since chlorine here is more electronegative, it will steal this valence electron from the carbon and bond there and form a chlorine radical, and then the termination step is when the two radicals, whatever they may be, join up and meet together to form a thing that is not a radical. So this can happen several ways, some of which are shown below. The next type of substitution reaction that you'll be seeing in the standard level syllabus is nucleophilic substitution with sodium hydroxide. So you'll only consider the hydroxide ion. Nucleophilic substitution is a big topic in HL, so we'll leave it there, but here's a potential mechanism. Bonus points to the HLs that know what type of mechanism this is. I'm not going to say what it is, but you can leave it down in the comments below, and I don't know, I'll give you an e-cookie or something. Lastly, we revisit benzene, and now that we understand sort of what a substitution reaction is versus an addition reaction, we can revisit the topic. I'm just reseating myself here to get myself more comfortable. We can revisit that topic that we discussed in the first video. So benzene undergoes substitution reactions, not addition reactions. An electrophile is an electron deficient species that affects, well, you don't need to know what it is, but basically the ring never breaks. The ring never breaks, and the reason it never breaks is because it's really stable. Addition reaction would cause the breaking of that ring, whereas substitution wouldn't, as we sort of just saw how they undergo. So substitution, you substitute something that was on the original hydrocarbon, whereas addition is you add to that hydrocarbon. Whereas substituting is you replace something on there with something else. That's pretty straightforward in terms of understanding. Um, Now the next bit we talk about is partial oxidation of alcohols, but before we do that, we need to first learn how to classify alcohols. So we can use the terms primary, secondary, tertiary, and quaternary to describe carbon atoms in any organic molecules, not just alcohols and allogen alkanes, but um, the ter- that term refers to how many hydrocarbon branches are attached to a carbon. So one hydrocarbon branch is primary, two is secondary, three is tertiary. So basically, the degree of hydrocarbon just basically asks how many other hydrocarbon chains are attached to this molecule. So one is primary is one, secondary is two, tertiary is three, like I said. And now that we know how to do that, we can now consider the partial oxidation of alcohols. Let me just see how long this video is. All right. So when we consider the partial oxidation of alcohols, um, you can oxidize them fully, which is just burning them, or we can partially oxidize them. So oxidizing means we add, in this case, we would be adding oxygen or um, losing hydrogen atoms. So this is where those alternate definitions for redox comes into play. So we also consider here that the number of carbon bonds the number of bonds to oxygen is also considered oxidation. So having a C, so comparing a C single O CO single bond to a CO double bond, the double bond is more oxidized than the single bond since it has more bonds to oxygen. And this is an important concept. So complete combustion of alcohols, that's just burning them in the presence of oxygen gas or a strong oxidizing agent. But now we consider the partial oxidation of alcohols, which is only oxidizing. Basically, this is the reaction mechanism that turns alcohols into carboxylic acids, aldehydes, or aldehydes or ketones, and this is how you go from alcohols to those compounds. So alcohols will partially oxidize in the presence of weak oxidizing agents such as potassium dichromate or potassium permanganate. Um, Acidified dichromate is only strong enough to oxidize carbon atoms that have a 1CO bond, but not strong enough to oxidize any carbon-carbon bonds. So it'll keep the carbon chain intact. However, it will oxidize carbons that have a CO bond. So this is sort of the next. So you need a couple of reagents for this reaction to occur. You can't just dump in the acidified dichromate. You need the reaction mixture needs to be heated up. You need acid. You need the mixture to be acidified, and you're expected to know that the oxidized color is orange and the reduced color is green. Chromate, the dichromate ion is reduced to green chromium ion, whereas chromium 6 plus ion is orange. You're expected to know that, and the higher levels are expected to know why that is. The standard levels, you're not expected to know why that is, but that's regardless. That's a bit off topic. So the reason why we discussed the degree of hydrocarbon is because this is where it comes into play. Primary alcohols, secondary alcohols, and tertiary alcohols will all react slightly differently to form different products. Primary alcohols and even primary alcohols, you can actually change what product forms depending on the type of conditions you perform the reaction under. So let's start with primary alcohols because they're the most complicated and it's easier to get this out of the way first. So primary alcohols can either be oxidized to form carboxylic acids or aldehydes. And the aldehyde is an intermediate in the reaction series, so it increases the number of C double O bonds, and it occurs in a multi-step process. Now, what if you could actually stop the reaction at the aldehyde if you set your apparatus up properly? Now, how do you do that? Note here that aldehydes, they only have dipole-dipole forces, whereas the carboxylic acids and the alcohol both can undergo hydrogen bonding. And that means that the aldehydes have lower boiling or melting points. So we can actually use the fact that the alcohol has a low boiling point. Um, we can use the has a lower boiling point to actually filter it out. So if we heat the reaction mixture just to the aldehyde's boiling point, uh, when the reaction mixture undergoes when the reaction undergoes, all the aldehyde will boil off, and then you can use a condenser to filter it out. So here is what we mean by that: a condenser tube where there's cold water flowing in and out here, um, and the condenser tube will cool the aldehyde down, and you can filter it off. Whereas if this would be called distillation. If we just wanted the carboxylic acid, we would let the reaction mixture undergo reflux, where you would the same sort of idea, but except that since the condenser tube is vertical, any aldehyde that condenses will drop back down and react further. So that's sort of the primary alcohol, depending on the types of conditions. So to summarize, primary alcohols will either form distillation if it's under is if, no primary alcohols will undergo partial oxidation to form aldehydes if it's under distillation, or carboxylic acids if you reflux the mixture. Secondary alcohols always form ketones, and tertiary alcohols will not react at all. Um, Lastly, we consider esterification reactions, which are um, basically the formation of esters, which the way you form them is you take a carboxylic acid and an alcohol and you combine them together and you get water and an ester. It sort of works like a acid-base reaction, whereas this OH and this H combine to create this H2O. They're also called condensation reactions because they're considered a type of condensation reaction because they form water. And yeah, that's really all there is to it. Um, and this is sort of why we name esters the way we do, because we generally name it carboxylic acid alcohol, because that's the way it works in the real world. So that is it. Thank you for watching. I apologize for the long video lengths, but they really are necessary, so thank you for watching.